Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. In the past few modules, we have been learning about paging, details about how paging is being done, how address translation is done in paging, and today also we will continue to learn about paging. The learning objectives of today's class are: we learn what hierarchical paging is, and we will see how shared pages are being utilized. And what is paging? We will have a brief introduction to the paging what we had been seeing in the last few classes. In paging, the logical address space or the user's address space is divided into pages, and the physical memory where the process has to be kept is divided into similar sized frames, and the pages or the user's pages, user's program or the user's file which has been divided into pages are placed in the frames in the physical memory. Now, to know where the pages are being kept in the physical memory, we need to have something which remembers about how the mapping is being done. So, for this we have a page table. The page table does the mapping from the pages to the physical frames, and we also saw the different ways in which the page tables can be implemented, and we saw that the use of a translation look-aside buffer increases the speed with which the translation or the mapping can be done from pages to frames. And then we saw that memory protection can be done along with paging, or you can have a few bits that are being placed in the page table which will help in the protection of memory. And we saw that there are different ways in which the page table can be organized, or there are different page table structure. So, the different page table structures are: you have hierarchical paging, you have hashed page tables, and you can have inverted page tables. In an earlier module, we learnt how hashed page tables are kept and also how inverted page tables are maintained. And in today's module, on today's lecture, we will see how hierarchical paging is being done. So, first, why is the need for hierarchical page tables? In modern systems, you have a very large address space. That is, the address space can have a size of 2 power 32 to 2 power 64. And when you have such a large logical address space, the page table becomes very large, and hence you can't place the single page table into single page in the physical memory. In an earlier case, if the page table is small, you can place the page table into a single physical frame in the main memory, but now it is not possible. So, what is done? The page table is now divided into pieces, or they are divided into multiple page tables. And now, for making the mapping easier, you have different ways. When you have a hierarchical page table, the simplest way is to have a 2-level page table. So, we will see an example and see how this hierarchical paging is being done. Suppose you have a logical address space in which the logical address is a 32-bit logical address, which means the logical address space size will be 2 power 32. And say you have a page size of 4 kilobytes. Now, this 2 power 32 sized logical address space has to be divided into pieces of or pages of 4K size. So, 4K is nothing but 2 power 12, K is 1K is 2 power 10, 4 is 2 power 2, so 4K is 2 power 12. So, this 4K page size is 2 power 12, and since the page size is 2 power 12, to address one of the 2 power 12 locations within the single page, you need 12 bits. Okay. So, each page, I repeat again, each page is 2 power 12, and hence you have 2 power 12 locations within each page, and hence to address one of the 2 power 12 locations you need 12 bits. So, the page offset will have 12 bits. So, if the page offset is 12 bits, this 32-bit logical address will now be divided into a page number and an offset. So, the page number will be 20 bits and the offset will be 12 bits. Now, when you have a page number of 20 bits, then how many entries will you have in the page table? If the page number is 20 bits, it can refer to 2 power 20 different pages. So, which means that you will have 2 power 20 pages and hence 2 power 20 entries in the page table. So, the page table will have 2 power 20 entries. And if each entry in the page table is 4 bytes, then each process will need up to 4 megabytes of address space just for the page table. How? Each page table entry is 4 bytes and you will have 2 power 20 entries in the page table, and hence 4 into 2 power 20, and hence you will have 4 into 2 power 20 should be the space that is occupied by the page table. So, you can see that the size of the page here is just 2 power 12, but the page table, the single page table is occupying 2 power 22 bytes of memory. This page table hence cannot be kept into a single page, or it will need a large space to be kept in the physical memory. So, what is done? This page table is now paged, or the has similar to how you paged your logical address space, or similar to how you divided your logical address space into pages. Now, the page table is now divided into pages. So, now let us just look at this diagram. You have different pages which have been placed in different places in the physical memory, and the mapping from the logical address space to the physical memory is kept in the page tables, and the page table is very large, and hence the page table is now divided into pages, and you have pieces of the page table, and each of this piece of the page table can be kept in a different place in the memory. So, now we need to remember, or we need to know where each of this piece of the page table is kept in the physical memory. So, for that we have another page table which is called the outer page table. This outer page table has got the mapping about, or has got information about where each piece of this page table is kept in the physical memory. So, the number of entries in this outer page table will be equal to the number of pieces that you have for this page table, or the number of pieces into which this page table is divided. So, in the example that we have been seeing till now, we saw that the page size is 4 kilobytes and each entry in the page table is 4 bytes. So, if the page table is 4 kilobytes, if the page table size has to be 4 kilobytes, or if each piece of the page table is kept or is accommodated into a page in the physical memory, and then which means that each piece can be of only 4 kilobyte size, and each entry in the page table is 4 bytes, and hence you can have only 1 kilobyte number of entries in the piece of the page table. So, if you have 1 KB entries in each piece of the page table, 1 KB is nothing but 2 power 10, then which means that you have 2 power 10 entries in each piece of the page table. Now, to address one of these 2 power 10 entries in the piece of the page table, you need 10 bits, because it is 2 power 10. To address one of 2 power 10, you need 10 bits. So, 10 bits are needed to address one of these 1 KB entries. So, now the page number that you had, that is 20-bit page number, is now divided into 2 parts, a 10-bit page number and a 10-bit page offset. So, earlier when we learnt about paging, we had the entire logical address space. The logical address space maybe was some 20 bits or 32 bits or something like that. That was divided into pages, and then to remember each of the page we had a page table, and hence we divided the 32 bit logical address into maybe say a 12 bit offset and a 10 bit page number. Very similarly, now since the page number is now divided in a similar manner into two parts, a 10 bit page number and another 10 bit page offset. So now the logical address will look something like this. You will have the 32 bit address being divided into a 12 bit offset that will be used to address one of the locations within a particular page, and then you have 10 bits that will decide or that will be used to address one of the locations within each piece of the page table, and finally this 10 bits will be used to address or will be used as an index into the outer page table. So, P1 is used as an index into the outer page table, and P2 is the displacement within the page of the outer page table, which is shown now with this using this diagram. So, here you can see that P1 is used as an index into the outer page table, and you get the address of where the inner page table is stored, and then use P2 as an index into the inner page table. You get the address of the frame where that particular page is stored, and then use D as an index into that particular frame to get the exact memory location that you need to address. So, here we have seen two-level paging. We will see one more example of two-level paging which is being used in the BAX architecture. So, this BAX architecture is a 32 bit machine, but here the page size is only 512 bytes. So, 512 bytes is nothing but 2 power 9, and hence the number of bits that will be used for the offset is only 9 bits. So, if 9 bits are used for the offset, you will have the remaining bits of the 32 bits, 9 bits will be used for the offset. You will have the remaining bits which can be used for the page number. But in the case of this architecture, they have a slight variation that they have done, in which they have divided the logical address page itself into 4 different categories or into 4 different sections, and they use 2 bits to identify one of these 4 different sections. So, 2 bits will go again to address one of these 4 sections. So, you have remaining 21 bits which will represent the page number. So, totally you have 32 bits, of which 9 bits will go for the offset and 2 bits will go to address one of the 4 sections. So, 11 bits, and from 32 minus 11, that is 21 bits will represent the logical page number. So, this is another example of two-level paging. So, 2 bits for the section, 21 bits for the page, and 9 bits for the offset. So, we will see another example for multi-level paging, where you have a 64-bit logical address space. So, the logical address space is very large here. So, 2 power 64 is the size of the logical address space. So, the page size here again is only 4 kilobytes, that is 2 power 12 bytes. So, if the page table is size is 4 kilobytes, the number of entries in the page table will be 2 power 64 divided by 2 power 12. That is, you are dividing the 2 power 64 sized process into pieces of 2 power 12 bytes or into pages of 2 power 12 bytes. So, 2 power 64 divided by 2 power 12 is 2 power 52. So, the number of entries in the page table will be 2 power 52, because 2 power 52 is the number of pages that will be generated by dividing the entire logical address space into pieces of 2 power 12 size each. And 2 power 52 is very large, because you need to have 2 power 52 entries in the page table. So, 2 power 52 entries in the page table, hence the page table size becomes very large. So, what is done? The page table is now divided into pages. So, if you are using a 2-level kind of paging scheme, if you are dividing the page table into pieces such that each piece will be accommodated in a single page, then you will have 12 bits for the offset. So, you have remaining 52 bits. And the inner page table is now divided into pages, each having 2 power 10 4 byte entries. So, now your address will look something like this. So, 12 bits for the offset within the page which is kept in the physical frame, and then the page table is now divided. Page table is now divided into pieces as very similar to the example that we saw earlier. You have a 4 byte entry in the page table. So, you will have 2 power 10 entries within each piece of the page table. So, 10 bits will go as offset into offset to be used to address within each piece of the page table, and hence the remaining 42 bits will go as the page number. So, now here you see that again this is very large. So, what does this refer to? When you have 42 bits as P1, there will be 2 power 42 entries in the outer page table. Okay. So, 2 power 42 entries in the outer page table is again very large. So, the outer page table can also be paged now. So, the outer page table is now again divided into pieces. The outer page table also will have a 4 byte entry, and hence this will again be divided into pieces such that each piece can be accommodated into a single page. So, dividing the outer page table into pieces such that each piece is accommodated into a single physical frame, then the mapping will be done something like this, or the address will be divided something like this. So, the 42 bits is again divided into a 10 bit and a 32 bit. So, you will have one more page table, another level of page table, along with this inner page table, outer page table, one more level you will have. So, your outer page table, but you can see that the outer page table is still 2 power 32 bytes, which is again very large. So, in that case you can go in for a 4-level paging scheme. So, 4-level paging scheme, but it is found to be too large. Some of the architectures have different kinds of paging schemes. Spark architecture supports a 3-level paging scheme, and 32-bit Motorola architecture, 68030 architecture, it supports a 4-level paging scheme. So, depending on the size, different architectures support different levels of paging. Now, we move to the next topic, which is called shared pages. So, we will see here how pages can be shared. That is, this is one of the advantages of paging, that is, you have a possibility of sharing code which is common. Say for example, you have an editor program, a text editor, and 20 users are using a particular text editor program. And the text editor has got 150 kilobytes of text code and 50 kilobytes for data. And this 150 KB of text code, if it is being kept as a separate, kept in separate pages for each of the 20 users, then you need 150 into 20, you need 4000 kilobytes to support 20 users. And for the data, you need only 50 into 20 space. But if this code of the editor can be shared between different users, then you can reduce can be shared between different users, you can reduce the amount of space that the code will occupy for 20 users. So, you can share the code if the code is a re-entrant code. What is meant by re-entrant code? It is a code which is non-self-modifying. That is, even while execution, the code does not change at all. There is no change to the code. So, if there is such a kind of a code, if there is a re-entrant code which will not even change even during execution, such a code can be shared between different users. So, look at this example. You have process P1 which is using an editor program, and the editor's code occupies 3 pages, and there is one page which will be used by the data by that particular process. And process P3 again has got 3 pages of the editor and some page for the data. There is another process P2 which uses 3 pages of the editor's text code and 1 page for the data. Now, this ED1, ED2, ED3 is a similar type of code and which is also a reentrant code. So, rather than having ED1, ED2, ED3 being kept in different places for each of the process, rather than making a copy for each of the process for these 3 pages, you can maintain a single copy in the physical memory for all the 3 processes. So, what is done? ED1, ED2, ED3 is kept in the physical memory, but the mapping is done properly in the page table of each of the process. So, each of the process has got its own page table. So, process P1 has got its page table, P3 and P2, each process has got its own page table. Now, ED1 is placed in frame number 3, and hence the page table for each of the process corresponding to that particular page ED1, their frame number is maintained as 3. And ED2 is kept in frame number 4, and similarly the frame number is maintained in the page tables for each of the process. Similarly for ED3 as well. Now, the data is but separate for each of the process. The data can't be similar for each of the process because each process will have its own data which will be varying. So, data for data alone, for P1 you provide frame number 1, for P2 frame number 7, and for P3 frame number 3 is provided. So, here you see that the space occupied by the text code is in the main memory is reduced because all the processes share the text code. So, if 2 or more processes can execute the same code at the same time, then the code is if the code is reentrant, the 2 or more processes can execute the same code at the same time, and the code will not change during execution. But the data will be different for each of the processes. So, the shared code, even if 20 users are there, only one copy of the editor is needed, only 150 KB is needed in the physical memory as we saw in the example. If we copy for 20 users, then you may need 4000 kilobytes, but here we have saved the memory space. But the private code and data will be different for each and every process, and the private code and data alone we maintain a separate copy for each of the process. But how do you share pages when you have an inverted page table architecture? We learnt about an inverted page table architecture in which you maintain only one page table, and what you maintain in the page table is you have an entry in the page table corresponding to a frame in the physical memory. So, for each frame in the physical memory you have an entry in the page table, and in each page table entry you maintain the page number and the process ID of the process which is using that particular frame. Say if this is the fourth entry or the fourth frame, then you remember that in the fourth frame in the physical memory, this page number P of process PID is kept in the physical memory. That is what is maintained in the page table. But now when you have such a kind of an architecture, it becomes difficult to share pages, because you cannot share pages between different processes. So, this particular page, if it is to be shared between different processes, then you may have to maintain the process ID of a number of processes which are all sharing this particular page, which is not possible in an inverted page table. So, when you have an inverted page table architecture, sharing of pages becomes difficult. You cannot share pages with inverted page tables. And in shared pages, that is because shared pages, multiple virtual addresses of different processes are mapped onto a single physical memory. But in inverted page table, there is only one virtual page corresponding to one physical page, and hence you cannot use multiple processes to share a page in the case of an inverted page table. Summary for this lecture: when the logical address space becomes much larger, then the size of the page table also becomes large. because the logical address space is divided into pages, and for each page you need to have an entry in the page table, and when you have more number of entries in the page table, the size of the page table becomes very large. So, when the size of the page table becomes large, it becomes difficult to accommodate this page table in the physical memory. And hence, what you do, this page table is now divided into pieces. Each piece will be the size of a single physical frame or a single page. And each of these pieces of the page table can be kept in any place in the physical memory. And to remember where each of the piece of the page table is kept in the physical memory, you maintain an outer page table. And it is also possible that the outer page table can become very large, and in that case you may also have to page the outer page table and maintain another level of page table outside of that outer page table. So, in such a case, in such a manner, you can have hierarchical page table maintenance. And sharing of pages is also possible when the text of the code is reentrant. Then the code can be shared between many processes. So, if many processes are trying to execute a similar program or a process, then in that case many processes can share the similar code, and you have facilities in the page table for sharing the different or sharing a similar code. But when you use inverted page tables, it is not possible to share pages. So, the references: acknowledgement. Thank you.